Okay, so this video is going to go over Laplace transforms and the basics for them. So, up until now, we've been dealing with solutions in the time domain, but now we're going to get solutions using the frequency domain. So, for an example system, let's say we have m d double dot plus c d dot plus kd is equal to 0 for our system. And let's say that we have three different values of c. C is equal to 0, the black line here. C is very large, which is going to be the red line. And then C is somewhere in between those two values. It's greater than 0, but it's not huge. Uh, the case for C is equal to 0 is obviously related to the frequency domain, but actually all three of these cases can be represented in the frequency domain. So what are the basics for Laplace transforms? Well, Laplace transform, it's represented by this L here in the brackets. The Laplace transform of x, some function x of t, is equal to, if you take the limit of large T approaching infinity and you integrate x multiplied by e to the negative st over time, you end up with this equation over here on the right side. So x of t times e to the negative st times dt, integrate that from negative 0 minus just a little bit before the beginning of time to infinity, essentially. This is a very compact way to write this. So s is our complex variable. It's going to be the guy that ties into frequency very closely, similar to how t relates to time, though it's not quite the same as that one-to-one case there. But let's say that we have x of t is equal to 0 for times less than 0. So no initial conditions for our system. If that's the case, then we can take this integral from 0 minus to 0 of x of t of e to the negative st times dt, and that's going to be equal to 0. Nothing is happening essentially before time. So now we can take our Laplace transform. Instead of evaluating from 0 minus, we just evaluate from 0. And a much more compact way to represent this system is our Laplace transform of x of t is just big X of s. And if we want to, we can also define our inverse Laplace transform, where our small x of t, our state in the time domain, is equal to the inverse Laplace transform of big X of s. So capital letters are generally going to be used to represent things in the Laplace or frequency domain. Lowercase letters like x of t, in this case, those are for the time domain. Now, some properties of Laplace transforms. So Laplace transforms have the linearity property. So if we have L, or Laplace transform of A times f of t plus b times g of t, you can take those a's and b's out of these functions and separate them, and you can also split them up into the two different pieces, f of t and g of t, separately. So we can end up with this Laplace transform here is equal to a times capital F of s plus b times g of s, for an example. Another example, let's say we have x of t, which is equal to some constant plus e to the negative at. Well, what happens in this case if we do a Laplace transform for this? I'm not going to go through all the little steps here to figure this out, but pretty much you can use that linearity property to split this up into two different pieces. And you can end up with a solution that this Laplace transform of a constant plus an exponential is going to be the same thing as a Laplace transform of that constant, or it's going to be the same thing as that constant over s. So essentially the Laplace transform of that first piece and the Laplace transform of the second piece. An exponential e to the negative at is going to be in the Laplace domain, or the frequency domain, 1 over s plus a. And in addition to all this, the inverse Laplace transform also has that linearity property. So if you have a Laplace transform that you're trying to, or something in the frequency domain that you're trying to get back into the time domain, you can still split up things, take out constants, and end up with the same inverse Laplace transform. So just quickly, here are some common Laplace transforms. So one of the most important are unit impulse. For any time greater than or equal to 0, let's say x of t is going to be equal to that unit impulse, or function that we've seen before. X of s, these are pre-solved Laplace transform solutions, is going to be equal to 1. For a unit step, which is going to look like essentially nothing before time, and then you step up to 1 and hold that constant. So a constant, for example, that's represented by u of s here in this case. And the Laplace transform of that guy is just 1 over s. So this is another pre-solved Laplace transform. The shifted unit step is another example where essentially you're just going to shift it by a certain amount of time t here. We have our exponential, which is one of our most basic cases. E to the negative at is 1 over s plus a. We also can do Laplace transforms for sine waves and cosine waves, which end up with what we have here. And notice that for this exponential here, it would lead to essentially an exponential decay for any a greater than 0, which is what we would expect for an exponential. Now, just a couple more important properties. The Laplace transform of a derivative, which is going to be very important. That's going to look like, so our Laplace transform of dx over dt, or x dot, is going to be equal to the Laplace transform of just x, which is going to be capital X of s, times s, minus the initial conditions. Notice that this is a lowercase x of 0. So that's our initial condition there. If we were to take the Laplace transform of a second order derivative, it would end up being very similar in that we take the Laplace transform of this guy here. So we'd end up with s squared times x of s minus s times our initial condition, the derivative of that state, minus our initial condition of that state itself. And we can go on and on with higher order derivatives. Now, the Laplace transform of an integral, that kind of works the opposite in that if we have an integral for x of s, our Laplace transform, instead of multiplying by s, we're going to be dividing by s. And then we have for, whatever our constant term is that we would have with integrals divided by s as well. Now, the final and initial value theorems are both pretty important and they're very useful. The final value theorem is used to find steady state. So if we want to know what x ends up with, like our velocity at the end of time for a vehicle, if we go on forever or until we reach steady state, we could evaluate that in the time domain, but it's actually much easier to evaluate it in the Laplace or the frequency domain. So if we take s, multiply it by x of s, what we're looking to get the steady state value of, and evaluate that as s approaches 0, we get our final value, what our steady state will be. Now, there are a few conditions to this. Our derivative of x and x must have Laplace transforms. X must approach a constant as t approaches infinity. So that's true if all roots of the denominator have negative real parts, which is something that we're going to get into later in the class. And now we also have our initial value theorem, and that is used to find x at t is equal to 0 plus, so right after the start of time. And it pretty much works almost the exact same way as the final value theorem, except you're evaluating s times x of s as it goes to infinity in this case. And now there are conditions with this as well. The limit with s approaches infinity exists. The Laplace transforms for both of these exist. And if x of s is a rational function, the numerator's degree is less than the denominator's degree. Essentially, there is a higher order term of s on the denominator than the numerator. You'll get finite results for this. And that is Laplace transform basics.